Welcome back to the Deep Dive. Today we're tackling one of the biggest questions out there. How did the universe first light up? We're talking about the very first stars, and maybe, just maybe, a faint signal from the dawn of time that could tell us about them.
Exactly. That's our focus for this deep dive, this incredibly subtle radio signal. It comes from, maybe 100 million years after the Big Bang. And the idea is it could hold the secrets, the actual properties of those first stars.
Stars we've never actually seen.
Right. We haven't directly observed a single one. It's a huge challenge finding them. So this signal, this ancient radio hum, is incredibly promising. It's like an indirect clue.
Okay, so let's unpack this cosmic mystery then.
Yeah.
Our mission today, follow the journey. From a totally dark early universe to one, filled with light. We need to understand what this signal is, what new research tells us about the fingerprint those stars might have left on it.
And crucially, how the next generation of telescopes might actually find it, how we can finally learn about these first lights.
Okay, so let's rewind. Billions of years, right after the Big Bang. What did the universe even look like? It wasn't stars and galaxies, right?
No, not at all. Think of it as this incredibly hot, dense fog, mostly plasma, basically. Atomic nuclei and free electrons all mixed together, completely opaque. You couldn't see through it.
Hot soup?
Pretty much. But as the universe expanded, it cooled down. And eventually, it cooled enough for neutral hydrogen atoms to form, plus a little bit of helium.
Okay, so atoms form.
Yeah.
But still no light.
Exactly. No stars yet. So what followed was this long period of, darkness. Billions of years, actually. The cosmic dark ages. It was cold, quiet, dark.
It's amazing to even try and picture that. A universe just waiting.
Yeah.
Before the first light switched on, that transition from dark to light, that's a fundamental shift. And yet the mystery remains. Despite all our telescopes, all our technology, we still haven't actually spotted a star from that very first generation. They must have been there. But where are they?
Well, the leading theory is that they were monsters, absolutely huge stars, maybe thousands of times the mass of our sun. Thousands. Wow.
Yeah, and being so massive means they burn through their fuel incredibly fast. Their lives were really short, cosmically speaking, a flash in the pan. They lived fast and died young.
Which makes them almost impossible to see directly now, I guess. They flared up and vanished billions of years ago.
Precisely. They're just too far away and too long gone for our current telescopes to pick out individually.
So, if we can't see the stars themselves, how do we find any evidence they were ever there? Is there like an echo, a fingerprint left behind?
That's where this 21-centimeter signal comes in. It's our best bet for a marker. It's this very, very faint radio wave.
Okay.
It's emitted by all that neutral hydrogen gas that filled the early universe. Basically, the electron in a hydrogen atom can flip its spin relative to the proton, and when it does, it releases a tiny bit of energy as a radio wave with a specific wavelength, 21 centimeters.
Ah, okay. So it's not light from the stars, but this background hums from the hydrogen gas itself. Exactly, a hum that was happening everywhere. But the key idea is that the first stars, their light and their radiation, would have influenced that hydrogen gas. They would have changed how that 21-centimeter signal behaved in their vicinity.
So the stars left their mark on the hum. They sort of modulated it, encoding information about themselves into this background signal.
That's the idea. This faint radio signal beaming across billions of years could have been affected in ways that tell us about those first stars, like how massive they were.
Which brings us to the new research. Because just knowing the signal exists isn't enough.
Yeah.
Right? You need to know what kind of mark you're looking for.
Absolutely. And that's the breakthrough from Thomas Gessie-Jones and Anastasia Failkoff at Cambridge and the Kavli Institute. They've done some really detailed modeling.
What did they find?
They modeled how the 21-centimeter signal would change
your source
depending
for
on
all
the mass
things
of those
2500.
stars. And crucially,
Today,
they showed
we're
not just
diving
that there
into
is
the
an effect,
ethics of
but
temporal
what
tourism.
That specific effect,
Welcome
that
back to
signature
Chronocast,
should look
your
like.
source for
So
all
we know what
things
pattern to search for in
2500.
the data.
Yes.
Today, we're
and what's
diving
really
into the
groundbreaking
ethics
about
of
their work is
temporal
that they
tourism.
included factors
Welcome back to
previous
Chronocast,
models
your
often
source
missed
for all
or didn't
things
model
2500.
consistently together.
Like what?
Today,
Well, the
we're diving
ultraviolet
into the
light from the
ethics
stars,
of temporal
obviously.
tourism.
But importantly,
back to
also the
Chronocast,
X-rays
your
produced
source for
when
all
these
things
massive
2500.
stars died.
Today,
okay.
we're diving into the
Or
ethics of
collapsed
temporal
directly into
tourism.
black holes.
Welcome
Yeah,
back
their
to
cores
Chronocast,
collapsed,
your
forming
source for
neutron
all
stars
things
or black holes.
2500.
And if these remnants are
Today,
in binary
we're diving into the
systems, pulling
ethics of
material
temporal
from a
tourism.
companion
Welcome
star,
back to
they can
ChronoCast,
become
your source for all
incredibly
things
powerful
2500.
X-ray sources, X-ray
Today,
binaries.
we're diving
Right.
into the
These
ethics of
X-rays
temporal
blast
tourism.
out into the
Welcome back to
surrounding hydrogen
ChronoCast,
gas,
your source for
heating
all
it
things
and ionizing
2500.
it in a different way than the
Today,
star's initial
we're diving
UV
into
light.
the ethics of temporal
Most earlier
tourism.
models hadn't
Welcome back to
properly accounted for
ChronoCast,
this
your
powerful
source for all
X-ray
things
feedback from the
2500.
stellar remnants.
Today,
So
we're
including
diving
those
into the
X-rays
ethics
gives
of
a much more
temporal
accurate
tourism.
picture of the signal signature.
Exactly. It changes the predicted signal significantly. By modeling the UV and the X-rays consistently, depending on the star's mass, they've given observers a much more precise target.
That feels like a really big step. It's not just theoretical anymore. It's giving observers a concrete thing to look for, closer to actually finding it.
It really is. It provides a specific prediction to test.
Okay, so we have the prediction. We know sort of what the fingerprint looks like. Now we need the magnifying glass, the tools to actually detect this incredibly faint ancient signal. Are we there yet?
Not quite there yet, but getting very close. We need a new generation of extremely sensitive radio telescopes, and they're being built right now.
Which ones should we be watching?
The big one is the Square Kilometer Array, the SKA. It's this huge international project with telescope dishes and antennas being built in Australia and South Africa.
Okay.
And there's also REACH-EH, the radio experiment for the analysis of cosmic hydrogen, which is in South Africa too. And precursor telescopes like ESCAP in Australia are already gathering data and testing technologies. These facilities are designed specifically with the sensitivity needed to try and pick up this faint 21-centimeter signal from the cosmic dawn.
Wow. So the technology is catching up to the theory. This connects right back to our mission, doesn't it? Using these new models to guide the observations from these incredible new telescopes to finally illuminate that dark chapter.
It's a unique opportunity, as Eloy de Lara Acevedo,
So, the latest
one of
data from the
researchers,
Kepler
said,
archives
these radio
suggests
telescopes could tell us
exoplanetary
details about how
atmospheres might
massive
be more
those first
common than we
stars were,
thought.
and maybe how different they were from the stars we see today.
Different how? Just bigger.
Bigger, certainly, but maybe also made of only hydrogen and helium, none of the heavier elements stars make today. That could change how they lived and died, too. We're trying to understand the very first recipe for stars.
And Anastasia Fialkov put it really well, too, saying, this is how we learn how light first emerged from the darkness, that whole transition.
From cold and dark to hot and bright. It's a story we're literally just beginning to piece together. This signal is a key part of that narrative.
It really is profound when you think about it. We're trying to observe the consequences of stars that died maybe 13 billion years ago.
Today we're delving into the mysteries of dark matter
Whisper in the
And how it
background
might
of
be
the
key
universe,
to intergalactic travel.
peering into that difficult-to-see early time. So let's recap this deep dive. We've explored how this faint hum, the 21-centimeter radio signal from ancient hydrogen, could be our key to unlocking the secrets of the very first stars we can't see directly.
Right, and new research has given us a much clearer picture of what fingerprint those stars, and crucially, their high-energy remnants would have left on that signal.
And now, giant new radio telescopes like the SKA are coming online, hoping to finally detect that fingerprint and measure the properties of those first cosmic lights.
It really makes you wonder, doesn't it? If we can learn to decode this ancient echo from the universe's infancy, from stars so different from our own sun, what other secrets are hidden in faint signals out there? What else is the universe whispering to us, just waiting for us to build the right ears to listen?
A fantastic thought to end on. Thinking about that incredible journey, light information, traveling billions of years from the Big Bang, from those first stars right to us, as we try to understand it all.
Welcome back to the Deep Dive. Today we're tackling one of the biggest questions out there. How did